All right, what is up? Today we're going to be doing our first static analysis officially. I got some notes here that I'll upload, put it to the GitHub, and we'll be on the virtual machine using VirtualBox. We're going to be using the terminal, we're going to be using LibreOffice Calc, and we will probably use Gidra after all this is done, just to confirm the flow and to finalize what we're looking at. So let's get started. So for reference, I'm using the Practical Malware Analysis book by Mikhail Sikorsky and Andrew Onig, and a foreword by Richard Betrich, I believe is how you pronounce it. I don't know where these names are from. That's just how I think they should sound. A static analysis. We're going to describe the process of analyzing the code or structure of a program to determine its function. The program itself is not run at this time, and here we want to identify the file format, the strings used, possible dependencies, and develop a basic understanding of the program flow. There's a few tools we'll be using, and we'll get to that. All right, so in these notes, I got a little pipeline for us. We're going to start with the file command, the readelf command, strings, xxd, objdump, and then we'll go to Gidra if we find it necessary. Xxd, objdump actually is going to do a lot of what xxd is going to do for us, as well as strings. But for strings, we can just get a quick output of the strings and see all of them. In XXD, we get a quick hex dump, and we can do some editing of the hex dump that we cannot do as easily with objdump. File is just going to show us the basic information. I'd say run this first just to make sure that it is an ELF. If it's not an ELF, you're going to have trouble with all of these actually, and you're going to probably want to go to your Windows virtual machine and do something a little bit different. Videos coming up on that. Then we'll do readelf to get some basic information. The -h is basically going to confirm what we got from the file output. Actually, I misspoke. Readelf -s is going to show us all the symbols. I will edit this and upload that again. All right, so we're back in the virtual machine. As you can see, I've already started the process here. I'm going to keep a Excel spreadsheet or a .obs or whatever you want to call this open, and throughout the process I'm going to just paste the results of important information I see, track the stack slightly, and then over here I'll track the program flow by just naming the functions and where the functions jump to. We'll see it as we go along. So with the file, we just go file, task, 5. It's going to give us all this information, the file format, the least significant byte first, if it's a pi executable, which means a position independent executable. We talked about that in the last video. The memory positions are adaptable, are not defined in the linking process. The x86 to 64, that's just the language, I guess, the assembly type. Version 1 is the ELF version, dynamically linked, which means there's going to be libraries that are outside of the function. The interpreter, also, this is actually also dynamically linked. This is for what it's for. It's not stripped, and this is the hash, which you can use this if it is malware. You can look up this hash and see if that hash has come up anywhere and has, but that is the file. You want to run this first, just make sure you're good to go. If you're ELF, you're rocking. All right, so now on to readelf, we can just readelf, display information about ELF files. So the file command is going to give information about the file itself and what kind of file it is. The readelf is more for what's in the file, going to give information about the contents of the file. Just kind of split up things and show them to you in a way that's easier to read than looking at the binary or the hex dump itself. So to start, readelf-h, and the capital W is just going to spread things out. This kind of confirms what was in the file information, except we get the entry point. This is where the start occurs, this is where the program starts. Then we get the start of the program headers and the start of the section headers. These are going to be, you're going to add this to wherever the initial point in memory is. Not this, actually. So this is an offset, and we'll see that once we get to the objdump. Little endian, that corresponds with the LSB, and the number of section headers, the number of program headers, flags, all of that possibly useful, maybe not. All right, then we get to the readelf-S with the W tag, so things go out wide. This AL portion stands for alignment, and that's the byte alignment. So to keep things in memory in order, they make sure that there is some alignment that corresponds with it. So if you have, everything's going to fit into the block of the alignment. We're going to keep things in that block size. So that kind of lets us know that there's going to be pieces of data in the text section and in the PLT section that are 16 bytes wide, which is a Q word. So that's useful. We might want to know that. Other than that, these are the section headers, and there's offset information. The text section, you can see this offset matches the entry point. Usually the text is where all the code goes. The PLT section, this is where all the headers and things like that, all the things that are outside that will be used potentially should be in there, and that's going to be on top of it. And the rot data, there should be something interesting in there. The raw data, the row data. So another useful thing just to see how big things are. So now we got some stuff to look at. We probably want to check out these addresses. And we can do an objdump, and that's going to show the disassembled assembly code. We're going to go -M for the Intel and -D for disassemble. And here we are. So we see these are the section names. This is the offset. We can see that main is 1145. But we start at 1060. Go to 1060, we see that this is the start. Disassembly of the text section, and that's where the code starts. This is where the program enters. The PLT section here has puts, which is how you print, and string compare. These are all part of external libraries. This is where all the external stuff is. And the init section, what we're going to ultimately do is go through the main and follow it and see if we can make sense of what the program is doing. And once we fill this out, we'll then open up Ghidra and confirm that we'll open up Ghidra and then we'll get actual values for these for these variables, and we'll be able to understand things a little bit better. And finally, there's the objdump-s. This is going to be what you can use instead of xxd. And it's going to show the contents, the hex contents of all the sections here. All the sections. I think the objdump actually skips a couple sections for some reason. So we can go through here. We can see that there's not much going on except in the row data, which is these are static variables. Global variables. There's a string that says this will never run. The strings will never be the same. Probably useful. It's at 2000. Okay, well then, yeah, it's at 2000. Then we got to go. This is 2000, so 1. It's at 2000 plus some offset. You got to count that. It's probably easier with xxd. So we can do xxd task 5 _ 1 and get the full thing here. Now they're broken up a little bit better, so it's easier to read, but they're kind of all smushed together. I think in the same order though, so we should be good. 2000, this is 1, this is 3, this is 5, this is 7, this is 9, so it looks like we started 2008 and go on from there, unless I counted wrong, which is possible. Now that we've done that, we know that there is something going on in the .row data 0x2000, and I think that's enough to start walking through here. We know that we're actually not going to walk through the stack in this way to initially set it up just to see where things are. We did this. We're actually going to go through the function calls, and I'll show that. So this is actually for a different file. I'll do it for this file, and I'll upload everything to the GitHub. The idea is we go through, we start at the main. We don't start at the start, actually. We start at the main, and we go through the main, and we follow until we get to a function call. And we either have an all true path, a false true path, all false path, and a true false path. For the false true path, alternates. So we go false true, false true, false true. And for the true false path, we go true false, true false, true false. And the all true path, we always go true, and the all false path, we always go false. That should cover us. We can put everything together. Technically, it doesn't cover us, but we can put all the information we have together. We go through and we go here. There's a jump above, and then we follow that. Then we go down, we follow that. And we get a pretty good understanding of what happens in the program. We can then use Ghidra to get the actual values for the string that's being used and the functions and other functionality. So I'll go ahead and do that for this new program, and I'll show you what I can amass or figure out without Ghidra. And I think this is a good step, because if you start getting lost with Ghidra, there's a lot going on. You can go back to this and get a good sense of where you're trying to go and what information you have. Okay, so we put everything in a tab format with a little spreadsheet here with some colors and just some information, the strings that come up, and the path. We have the all false path, where there's actually only one conditional, and that's false here, and the all true path, there's only one conditional, and that is true here. We pick up three sets of string. We have this string here in the blue, this string here in the purple, and this string here in the red section. We can go to xxd and see what those are, but it looks like, just from looking here, we have a call that does a string comparison, and it compares the RDX or the RSI to the RDI, which was originally the RDX and the RAX. And in the RDX, we moved, in the RAX and the RDX, we moved larger string. But then we come down here and we move the string at position 40, RAX into position 40, and RDX into RBP minus 38. These are hex numbers. keep that in mind. So we can go to RBP 20, and that's the first one. That's the pointer to the first one. And we see that that's going to be in RAX, and 40 is the second one, and that's going to be in RDX. So we're comparing these two strings. And it's backwards because of the endianness, but it looks like we have go faster with an exclamation point and a new line, and go slower with an exclamation point and a new line. And we have this string here at 2008, which we can see with XXD here, and go to position 2008. It also just so happens that the string date is at 11.5b, so we can check that out too. So 2000 and 2008. This will never run is 2008. That's what you get in the all false path. And in the all true path, we get 2020, which actually starts here, and the strings will never be the same, which is interesting because here the comparison is that they're not equal is true, and the strings will never be the same. When they are equal or not equal is false, then this will never run. So that's basically what we can pick up. We can go to 11.5b here, or just 1150, and basically we got go faster, and there's some, this is just nonsense from the this is just nonsense, but this is the string portion that we're looking at, and you can see here, if we start here, we get 476F, and it goes on till 65, which is right here, and we read the number, we read 2 bytes at a time in order but backwards. So we go 47, 6F, 20, 66, 61, 73, and so forth. So we're definitely doing a string comparison. We have all the strings we want. It looks like there's no input, and if it is good, we don't hit the conditional. If it's not equal, we print out a string, and if it is equal, we print out another string, and then we call the 1030 the puts here again, and that is going to print the string that gets loaded up here, which is this. This is actually probably too high, and we call that, and then the puts just puts out output on the console. So that is the static analysis. And finally, we can open up Ghidra. I'm not going to do a Ghidra walkthrough right now. That's coming up. First, I should probably go on Windows and do the same thing. We have a few more tools available to us on Windows, but as you can see here, Ghidra is pretty much a cheat code. We can go to the function sections, go straight to the main, and have it decompile the main for us, and it'll tell us everything we would want to know. In this particular program example, we're not moving stuff around, and everything's already predefined. But once you start, doing some input, maybe going outside of the file, maybe doing some directory stuff, it can get pretty convoluted because everything's undefined and the names are all weird, and it doesn't hurt to do this. Especially, you can copy and paste, I think, if I don't have it open, but if you can copy and paste this output here from objdump, and if you, one of these, what do you call them, large language models, pick any one, and just make sure you set up the table, give it the table instructions, tell it that you want to make a table, give it an example of what you want each cell to be, then you can copy and paste this in there, and it should convert it to a table for you pretty easily. I would say making this took about a real 30 minutes, and most of that was just coloring, getting the colors right, and copying and pasting the strings, and then checking that they were all right. So, and this was, it doesn't take, I would say it's 01 complexity to do this. Like, the larger it is, it doesn't take any longer, because you just have to go through and make sure that all the numbers match up. So maybe it's, it doesn't take that much longer. So maybe it does take a little bit longer. And if there's multiple functions, yeah, so it does, this process does take quite a while, so it's your call. But for some, it's a good idea. For this, Ghidra's a cheat code, and you can see here we got the 2 strings. So pretty much that is it for this video. I want to keep it short. Hopefully we're good, and we'll do Windows next. So hope you have a good one. Peace.